Hello, we're group 9 and this is going to be our video for our final project presentation. So our final project is a solar tracker and this is our model right here. So I'll just explain the basics on how this model is built and what we are going to go forward with. So I'll just move to the CAD portion of it. We had certain components here that were 3D printed. These are the 3D printed drawings that are shown here that we got it using the Ender Saturn 2 that is in the lab, is in Dr. Giankelly's lab. And so all these portions have been 3D printed with PLA and have been attached to the setup. So if you can see, this is the base along with the servo mounting pin. So that is here, this is that. Second is, this is another supporting unit in which one of the servo motor goes to, which is right here. And you can see there's a servo motor down there. And the third part is this extension. That is another extension for holding the servo motor. That pops in here, right? You can see that servo motor is attached here. And then the fourth extension is this. This is just used for shielding the photoresist in our connection, basically here. So going to this model, so I'll just explain what 3D printed parts were. So I'll just try to explain what exactly we'll be doing here. Just going back to the model, just in case. So this is the Tinkercad model that we have here. So in this model, we're starting off the Arduino Uno, the kit that was given to us for Team 9, and we're using the components that are provided, that are 2 servo motors. So we had one additional servo motor taken from the lab. We just need a regular breadboard, 4 photoresists as well as 4 resistors, and along with that, another solar panel for generating energy. So the main goal of this project is a sustainable environment where we can generate energy, as in. So if you look at the setup, so if you look at a regular solar panel, just in case, so whenever there's sunlight directly falling on the solar panel, it is going to be very efficient. But the sunlight doesn't stay at one particular point throughout the day. So the sun keeps moving from east to west to east, east to west, right? So because of that, you have like rays falling at a certain angle, which is going to make the solar panel very little effective. So it's not going to generate that much amount of energy. So for that, you need to make sure that the rays coming from the sun are totally perpendicular to the solar panel. So in this case, this is what we came up with to go ahead with that. So our solar panel setup has a movement of rotation of 180 degrees. So it has 2 servo motors. So it moves from both X and Y direction, and it moves along with the Z direction. So it does a 3D motion, and it completely has the capacity to follow the sun when it's fixed to a position. And by using this, we can make sure that the sunlight is totally at an angle of 90 degrees falling on our solar panel. So why that? I mean, would it be very little effective to do that? Because to move the solar panel, we do need energy. But then after like doing certain calculations, which we have added to our report, you can have a look at the calculations there. We found out that using a motorized setup to move the solar panel and following the sun is going to actually like consume less energy than that is being produced when the solar panel follows the sun. So this system is way more effective when it's used rather than a single solar panel just attached to the ground. So we have just gone through the basics. So I'll just explain the connections. So here I already explained this. This is our electrical diagram shown here. And we don't have many components for our system, but then it's a very complex system to analyze and break down. So going forward, this is how it is 3D printed. You can see the breakdown in the Ender. That's pretty much it. And this is our setup. We have a setup here as well as photos of our setup. We try to make sure that our setup is as light as possible. So we just made sure that our essential components are 3D printed, and we kind of use like very light cardboard sheets because to make our system as light as possible, because by using say 3D printed PLA even with very little infill is going to be very heavy. So this is just a prototype, and as we're using Arduino and the regular ST90 servo motors, which are not really that powerful, we want to make sure that it is as efficient as possible. And then yeah, let me just go ahead with the code. So I'll just move to the code section of it. Okay, this is our Tinkercad model. So basically us running that on Tinkercad. I'll just start the simulation here. So yes, the simulations here, the servos have moved to the 0 positions. And then you can also notice that the solar panel generating a 5-volt supply. So this 5-volt supply, what we're doing right here is we're just connecting the inputs of the solar panel directly back to the Arduino Uno. So our solar panel is going to power up the Arduino Uno system. That's how efficient this is. So as a future learning, as I already explained, I already told it produces more energy that is being consumed, because this Arduino is not always in operation. It just has to follow the sun, and every time the sun moves, it doesn't move that regularly, right? So every time the sun moves, that's when the energy is used. The other part of it can be used to store energy. So that is out of the scope of our project because that's really complex. We have to create a data logger, but then we're just showing possibilities from our side for this project. So if I show you in this, so as the simulation is running, I'll just try changing probably the value of the photoresist. So you can see if I move this to one particular angle, you can notice that my servo motors are moving accordingly based on the intensity of the light generated on one of the photoresists. So it can be one of these photoresists. So the sunlight is intense on this side. So if it's falling here, that basically implies that here it's really high. So our servo motors is going to move in such a way that the solar panel comes up and it falls direct to the sunlight, basically. So this is our project. Just going a bit deeper into the code, I can probably try explaining the code to you. So the most complex part of our project is definitely the code and not the connections. The 3D prints were hard because we had to indigenously design it for movement, but the code is the hardest part. Let me explain the components of the code. So These are just like, for LDR stands for photoresist. These are just photoresist connected to input pins, nothing too complex here. The other input that is the up-down servo motion and the left-right servo motion. So that is basically the input to the servo motors. One of the servo motors moves in the left-right direction, the other one moves in the up-down direction, right? So that's that. Then the next one is the threshold value. This is the most important point of our, say, the whole setup. Because this threshold value always has to be calibrated and set up for a particular area that you're working in. Because this is the threshold value of the photoresist. So whenever the intensity of the sunlight or light is higher, the threshold value goes high. So at this point, say I keep it in sunlight on outside conditions, and the intensity of the sunlight is 100, right? When it falls directly to the photoresist, that means this experiences an intensity of 100, but the other sides do not experience an intensity of 100. So what we have to do is we have to make sure that the threshold value is set below the one that is being recorded here, but also above the ones that is being recorded here, right? So only then this has to move. So this is what our threshold value signifies. The second one is the step size. The step size is for stepper motor movement, and every movement of the stepper motor follows a 180-degree loop. So if I have to move it, here I've given 5. So basically it moves at a 5-degree step, basically. So if it increases, if the step size is higher, the input to the motor, the servo motor, is very high. So it provides a lot of load to the Arduino. So for our DIW small system, having that much load, connecting 2 servos to one Arduino is going to kind of overload the Arduino, and it's going to start acting crazy. It's not going to move properly. So that's why we kept the step size fairly small. Now, just going to the basics, it's this serial beginner 9600 just for a serial monitor, nothing too complex here. And then this is basically just showing our LDR input to the analog reading outputs, basically. And now this is another formula that we came up with for the movement of the photoresist, for the movement of the panel. So how it calculates is, first it kind of finds out the average values for each region, because you're using top down and using left and right. So you can see here, so the average of top is calculated, the readings of the 2 tops are calculated, the readings of the 2 bottoms are calculated, readings of the sides. So all these averages are calculated, and based on that you're getting a differential value. So that's for the algorithm to run. So this is a part of a code that we had to work on, and just make sure that the formulas were right so that we don't mess up with the threshold values. The second is basically just the step size movement. As I already told you, the step size we have set it as 5, and the angle of movement is 180. You can notice the formula they're given is 180 minus step size. So for every run, it's like 180 minus step size, goes to 175, goes to 170, go to 165. So for the movement, so that's how the algorithm works. And basically, we have a look at the threshold value. For any kind of movement, the threshold value is going to play a huge effect for cutoff. So whenever it falls below the cutoff of the threshold value, like if we have like only one region having more than the threshold value, it's not going to move. But then when 2 regions have more than the threshold value, it starts adjusting itself so that it moves to an area where only one region has a threshold value. So basically, that's how it does. And so this is our code, and we have also added a delay of 20 milliseconds so that we have enough time for the Arduino input to work, because as we know, during indexing, if there's no delay, the steps is going to get cancelled and it's going to start lagging off. So this is our project. This is basically it. We kind of use like 2 light clips here just to add like weight counterbalance, because we kind of noticed that the 3D prints were not holding through that well. We did use PLA with high infill, but then yeah, that's pretty much just a modification. These are our connections. It's the same as what was shown in the Tinkercad model that was shown here. It's exactly the same. The photoresist, the inputs goes to each of the photoresists, and each of the photoresists is connected to the resistors here. You can notice the resistors are put here as well as the photoresists are here. So it's exactly the same as what is here. And as we have already shown in class, the system works pretty well, but it has to be calibrated for every type of movement. So the video is already shown in class. We'll also add some videos here that will be done over by Sujana. And thank you.